I'm sorry about that.
Yeah, we know what it's like. Oh yeah, he decided to take any work that was left over.
Yeah. Saturday, we started working on Saturday. We were group texting. We
started Sunday. We said we were going to do it Friday after last week. We went to eat and we're like, let's just go home.
And then Sunday, we just like, oh, whatever.
Time to start Sunday early.
No, like,
I started at
yeah, around 3. Everyone was just like, whatever, everyone just do something.
Yeah. But we all read each other.
and I'll print it.
Saturday told us, hey guys, I'm in a meeting. I'll catch up with you guys later. How cliche is it? Later Saturday, it went really long.
All right.
I'm going to come.
Let's just get it over with, people.
So when you guys
Show Monday, little show Friday, huh? All right, come on, guys, gotta get going.
oh damn, so you get
All right, so Sumner, you guys mind if we ended early today? Woo! For the first time, right? I've only got about 3. Come on, all right. I've only got about 3 pages of material today, and I noticed that we're actually 1 full day ahead of the calendar. So I don't. But really, what guys? All right. So we're 1 day ahead on the calendar. So we'll apply just. Normally, I would probably start on a new thing as a result, but I really feel like it, especially with warm air, so it gets to me too. So we'll end a little early today. I can't tell you a little, I wrote half the test. Again, I'm going to go over a lot of it on Wednesday, especially any example problems that I have from this stuff that we started on last time, this Henry's Law and Newton's Law stuff. I did work a problem, but I don't, with Henry's Law constant, I don't have a question like that on the test as it stands, but I'll let you know Wednesday whether I decided to put it on there. All right, so another thing to note that the unit section is now gone. If you don't get it about units yet, then you're kind of screwed anyway. So there's no point having it on the test, but you're all doing very, very well. All right, so there's no unit section, so I increased the size of the true and false. And overall, it's still a shorter test by about 2 questions, so that ought to help. So again, we have true and false, then we have homeworky problems, like the inverse and everything, with a certain number that you have to answer out of the total, and of course 2 derivation questions, and an extra credit, which is, pretty decently difficult, but a lot of you got it last time. So again, slightly shorter test, but bad. Remember that most of this material has been continuous, which means it's just a bigger pile of stuff now, and that's going to make it harder. Right? Overall, I do find the test to be harder. So, but again, that's just a natural thing because there's more material. And it doesn't help that it's all really fairly closely related up until this stuff we're doing now. So again, I'll let you all know quite a bit more on Wednesday when I finally finish with it. You guys, any questions from you folks up there?
Will you guys in a Carnot cycle?
Well, no, the Carnot cycle was last test. Now, final, could be on the final. Right, any other questions? So we're gonna, it starts at entropy. So remember, I ask a lot of entropy questions, and a lot of derivations are either derived this about entropy or hold it, the x dy at constant s. I added a few of those. So, also note, I did email you logged in. Remember, if you're not getting my emails, tell me. I added a lot of handouts, and one of them are example derivations. Some really, really hard derivations. If you can nail those, you're going to be able to nail anything. So, there's that. Anybody else? We're okay? Another question.
You briefly touched on efficiency. You're going to touch on that in the next example.
Say again?
Efficiency. You're going to touch on it in the next example.
You mean Carnot efficiency?
Just efficiency in general.
No, I only did Carnot efficiency, and that was last test. Again, a possibility to put it on the final, but not this next test. So remember, basically, I guess everything after Carnot. So maybe look at the Carnot efficiency and go from there. That's a definitely safe bet. I can't quite recall myself. So any other questions? Because we kind of have time. So, all right, if not, well, let's just go into old material. Again, I promise I will go over on Wednesday what of this stuff will be on the test, because I have 2 or 3 more questions to write, and they may go here. And definitely look for one of these Henry's Law, Raymond's Law on the true and false. I'm definitely going to add it there, and I may stop there. I just haven't figured it out yet. But anyway, okay. So remember that when it comes to partial pressures out here, I'm kind of starting out wrong. Let me go back and point out to you that kind of painful derivation that we did. I'm sorry, I shouldn't be talking about this right now. And don't write this down if you already wrote it down, or write it down if you like. Remember that this is, sorry, I'm kind of small. Delta H minus T delta mix S. And we know that delta mix S could be positive, but we make approximations. And we say that this is 0, and so this would be an ideal. Ideal equation, and based on delta S, I'm not going to do the derivations that I did last time. We get nRT. Now I have to have 2 contributions because I'm going to mix 2 liquids. I'm always going to stick with just 2 liquids. And then I have to add in the same for B. And recall that this is just minus T times the change in entropy. And we solve that 2 different ways to come up with the same equation. And there you go. And what this says, here, I should write this down. What this says is that according to this, everything will mix. Because these mole fractions are always less than 1, and the natural log of a number less than 1 is 0. 1 is always negative. So this says that everything mixes with everything. And this came about because of an approximation we made, and that was that the partial pressure, and I'm just sticking with D of A and B, is equal to the mole fraction times the pure partial pressure. And so remember start with pure partial pressure. You might want to write that down. I'm not going to write it down, it's too much. So, so this is an approximation again, and it's actually horrendously bad. It's an incredibly bad statement to use to say that basically, remember that we're hijacking equations for vapors, for entropy of vapors, and if this is the mole fraction in the gas phase, then I've got a great equation for mixing of vapors. The approximation is then to say that we'll stick with 1 mole of liquid, so therefore this is the same as chemical potential, and therefore the change in chemical potential, and say that this mole fraction in the gas phase is the same as the mole fraction in the liquid phase. Horrible, horrible mistake. Right, so, well, not the worst thing in there. Again, it'll work well for, so this is for, again, ideal, sorry guys, write that down, ideal solutions. And remember, ideal solutions mean there's no change in volume, there's no change in U upon mixing, there's no change in H upon mixing as a result. I proved that last time. And again, this will work well for like O-xylene and P-xylene and hexane and heptane, and maybe like ethanol and water, but nothing else. And then also, I'm fairly certain not all solutions mix. All right, this says that they do. So this is really horrendously in error. So now, here's a question I'll have. Okay, here's a good example of a question I could ask. All right, I mix 2 solutions, and I measure the vapor pressure of the vapors, but I have a can, I've mixed in 2 solutions, I won't say what, and I have a little sniffer, and the sniffer says, well, component B, I smell a pure partial pressure of A, so its partial pressure is its pure partial pressure, but I measure no pressure of B. So what's happening? All right, so, what's that?
B has a higher density, so it's trapped at the bottom of the A.
Well, so are they mixing?
No.
No, they don't mix. Right, now if you think about it, natural log of 0 is minus, so I said B, right? So sorry, folks, look at that, that's a mistake, I B. Technically, natural log of 0 is minus infinity. So this thing says that, of course they mix incredibly well. It almost exploded with energy. And obviously, the reality is, obviously B didn't mix at all, and it's sitting at the bottom. So remember those drawings I did last time showing why this is really a bad mistake. All A's on top and all B's on bottom. The B can't get out of solution to form a vapor. That's why you don't detect any vapor, because you put something on top of it. You capped it. So anyway, today we're going to fix this, and we're going to let this be something. And anyway. And so remember that when it comes to the partial pressure of the vapor, this whole ideal thing, and this approximation is Raymond's law, says that and this is a line, right? This is a line that goes from 0 to PD star. 0 to PD star. Oh, I should mark that as being 0. Well, whatever pressure unit, bars, whatever. So this is a line that goes from 0 to PB. Now, what I've drawn here is one example of a possible reality where there's actually some curvature to it. Now, in the limit of the solvent being mostly pure, you see that Reynolds law, meaning ideal solution, is pretty close. And then you deviate, and then when your solvent becomes a solute, then you're going to make this linear approximation and just replace PB star with so for an ideal dilute. And again, that's the Curdy curve. You say solvents follow Reynolds, and I'm not saying that correctly. The solute follows Henry's law. Henry's law. That's how we spell law, and that is that the pressure. So I wrote that here. Equals mole fraction. I already wrote this. So what you're doing here is you're just simply going to replace the partial pressure, the pure partial pressure, with the number that makes it work. And now, of course, and I mentioned that I really don't like this, and I don't even know why I would dare call it the law. And of course, you're completely missing this region here. So what the hell is that? Right, so this is, this is just making up numbers to make theories that we have work. And it's not because the theories aren't right, it's just that there's things that go into them that we can only know by measuring them. Or maybe there are more advanced techniques, but you know, that's kind of more of a grad school thing. And you're seeing this for the first time. So anyway, okay, that's mostly review. I do have one other question about Henry's law, which is actually really kind of important, and that's diving. And I think all of you know that you can't dive too far, or you're going to kill yourself. Let me show you what pressure is a function of depth. So I'll do this in kilopascals. So under the sea, start a new line under the sea at 0 elevation. Screw this up. Pressure in kilopascals is going to be 100. And then you swim to minus 10 meters, and the pressure is now 200 kilopascals, and then you go to 20, minus 20 meters, and now your pressure is 300 kilopascals. So you're really swimming with the fishies. And so I want to work a problem where 90 kilograms of water goes from let's see, I'll go from 20 meters to 0 meters. What does 90 kilograms of water sound like to you? What's that? A lot, yeah, but what's it a model for? Yes. 90 kilograms, it's about 150 pounds. A person, right. So a person, 90 kilograms H2O. The diver. Okay, so let me show you now we did this last time. Unfortunately, I was kind of rushing there because I know I got over. Let me show you an easy way to do this problem that's a little bit better than I did last time. And remember, when you look up Henry's law, it doesn't tell you what's what, right? So we had to walk through that last time. Okay, now here's a clever thing you can do that makes this question a lot easier. Now, air is about 75% nitrogen. So 75% of 300 kilopascals, that's a depth of minus 20 meters. Oops, why did I do that? Minus 75%. So we're figuring out how much nitrogen of 100 kilopascals equals, and again, just, check your calculator, 0.087 moles. Now, of course, I know that that's moles of N2. And then I just did perfect gas law. I found this to be 2.1 liters. 2.1 liters of gas. Okay, so you all know what happens when a diver has been at 20 meters, minus 20 meters, is there for a while and comes up, what happens? Ears pop? No, this person's going to explode. If you can't have 2.1 liters of gas suddenly show up in your blood and not explode, they actually explode. And the way people found this out was, anyone know what a diving bell is? Probably something you thought of as a little kid. This is what I thought of it. So under the sea here, what you do is you have a rope and this concrete, literally a concrete bell, which has a floor and a hole in it. And so then you get people, I can actually draw it better than this, and what they do is they go out and they can dig. So when they're making the Brooklyn Bridge, they had to build foundations under the Brooklyn Bridge is actually that's the East River, it's not the Hudson River, so I'm half from New York. So anyway, they had to dig out the bottom of the river floor and pour concrete, and I don't quite know how they did that part, but the way they got there was by these diving bells. I mean, pretty primitive, but this is 1800 or something, 1890. I don't quite remember when they built the Brooklyn Bridge. The thing is, when these guys came up, they started dying, about 50% mortality rate. That was a little too high to live with, right? These guys were, 50-50, they knew they'd come up, they were going to die, and no one had any idea what was happening. Until it was actually a local chemist figured out that they were under so much pressure. And remember, the water pressure is actually going to be defined by, so there's air in here, and you can see that the air, since it always wants to go up, this is why they can stay underneath, at least for a little while. And the reason that the pressure is what it is because it's actually pushing right here at the little hole where they dove out. That water is pushing into it until the atmosphere here was at 300 pascals. And the guy figured out that more and more gas was dissolved in their blood the longer they spent. So these free divers, they can get to these depths and better, but they have to come back immediately. It's because they didn't have enough time for nitrogen to get into their blood. These guys were down there for like all day, so there was plenty of time for nitrogen to saturate their blood. That's why they died when they came up. So anyway, I just thought I'd spread the horror. And the reason that now the way we avoid this actually is instead of, so most of your air is not breathable, right? You can't consume nitrogen. Some rare cyanobacteria can, but not you. So instead of 75% nitrogen, what you do is you insert your own gas that's 75% helium, and helium has half, I won't write it down, has about half the Henry's law constant, and so half as much air gets in your blood. Now still, if you come up, and so instead of 1.05 liters, that still will kill you. So when divers have been down for a long time, they have to go up to decompression tanks. They have to spend a week or two slowly decompressing so their blood doesn't explode. God, what a mess that would make. And someone has to clean that up too. Anyway, that's horrible. Okay. Anyway, so no more horrible death cancer, at least for today. New material is talking about how you take those numbers in the back of the book and start changing them. And basically, I'm going to take this equation here. I'll just rewrite it. And what I'm going to do is I'm going to divvy it up. I should leave it, but whatever. I'm going to divvy up those natural logs into a part for A and a part for B, and then I can say how those numbers in the back of the book, the table in the back of the book change. Here, I'll write this down. So G is nRT, IA, ln IA. So again, the point now is that this is for a solution of A and B, and my system is composed of the sum of the two. Oops, there we go. Okay. Now what I want to do is then divvy that up for A. So what I'm going to do is I'm going to go with the table in the back of the book. And I really should be adding delta formations here, but I'm just going to not do it just for the hell of it. And then I'm going to perturb it because it got mixed. A, L, N, I, A. And now what I'm going to do is put these two together. This is much better. Okay, again from the back of the book, plus N sub A, sorry. So that's a little bit more obvious. Oh, that just looks awful. OPCD today. Okay, there we go. NRT, LN, IA. And then, of course, the same for B. And I don't know why I'm not writing it down. It's kind of stupid, waste of time, but I can figure that out. And then all I have to do is divide by the number of moles to get chemical potential. And chemical potential is everything. And I'll just write that down. And I won't do B. Here, let me do it right here. I'll just say it's the same for B. So therefore, chemical potential of A is just RT. RT, LN, Ka. Right. Whoa, no, I made a mistake. Didn't I? It has to be the number from the back of the book divided by 1 mole. Remember, those numbers in the back of the book, because they're per mole, are actually chemical potentials. And again, the point that I brought up a long time ago was that those are for pure substances, and when you get things to react, they're not pure. Okay. And, yeah, same for B. I won't write it down. So now what I want to do is make a little table. I'm going to partially fill in the table, and then we're going to pretend what happens to see what we get when we don't necessarily let down to HB0. And then we'll take a break, and that will be it until Wednesday. So here, I'm going to say what? And just to summarize, so we have solutes and solvents. And solvents. Solutes and solvents. And if what is an ideal solution, that means Rayleigh's law is followed for both, and therefore solute is A. Therefore, this is still true. Again, remember the star is the number in the back of the book. RT, LN, IA. And the same for the solvent. Sorry, I know this is kind of boring. I told you I didn't like this stuff very much. It's awful dry. So, okay, so ideal, then we have ideal dilute. So this is something different. So I'll just mark that. Ideal dilute. And that means that the solvent still actually follows Rayleigh's law. And so that's for here. But this guy, the solvent, follows Henry's law. That's for this guy. Now remember that, don't forget where this equation came from. I probably should have redone it. But what happens to the chemical potential of A, it's still equal to the number in the back of the book. Sorry, in the way. Plus RT, natural log. Now remember that I got this Ka by using Dalton's law, that the partial pressure of B was just the mole fraction times its pure partial pressure. Now it's fine for a vapor. It's no more an error than the perfect gas law, which is actually really quite good, to be bloody honest. And so what we did was, instead of the pure partial pressure, instead with Henry's law, you just put in a constant. There you go. And remember, that's because the partial pressure of A is now its mole fraction times a constant. And that is Henry's law. So that's where that comes from. Okay, last bit, and we will break early. And I'll probably just try to slow down a little bit in the next section. And also, I know this class seems to go on forever, but the reality is, you're on your what problem set? 7. You know how many there are? Wishful thinking. 10. No, you can't shout me down on this. Everyone's writing them. There's 10. Now remember the tests are based on the problem set, so you do want these actually, right? So only 3 problem sets and we're done. Okay, okay, let's do the deviations. So what I'm doing here, come on, people. What is that little guy's QT star? Mole fraction will be 0 to 1. And vice versa. So again, what about these regions, which Henry's law and Orient's law seems to apply? So again, this is something I really don't like. Activity. Okay, seriously, what you do is you say that activity of, let's say A, is the mole fraction of A times a nameless constant. Unitless constant as well. So in other words, so what do you do with this? So again, our equation for delta G is just wrong. And it can be badly error. If you actually look at real numbers, I've looked them up, I won't bother you with them. It doesn't matter that much, but I've looked up actual numbers for these mixing delta G's versus what ln chi A would predict. And they can be way off sometimes. So, anyway, so there you go. And then you do the same for B. For chi B on activity of B. Which is defined the same way, obviously. Okay. The fact that I represent A this way is going to be used in one more second. But notice that what I've done here is that approximation of the mole fractions of the vapor are the same as the mole fractions of the liquid. It's a horrendous thing. It's wrong. It sets this thing, everything mixes, which is just obviously crap, really. So what do you do with activities? These are numbers that make it work. That's all that it is. It's a correction factor so that the equal sign still works. And you make this gamma, this representation, I'm going to use it in a minute, this means nothing. It's just gamma can be whatever it needs to be to make this work. So it's just a boo-boo, it's a boo-boo. The equation doesn't work, so this is the artificial fixer. You know activities by doing the experiment to begin with, which is cheating, essentially, from a physical chemist standpoint. Because in physical chemistry, the whole point of all of this is to not have to do the measurement to begin with. And that's two reasons, right? I understand everything, which is awesome. Number two, I don't actually want to spend all day mixing things and measuring their delta G. That kind of blows, right? That's a very costly, long time activity that may be necessary, unfortunately, because I don't have better answers. But as a physical chemist, we'll be trying to look for better answers than none whatsoever. So again, one of my philosophical problems with this. Now this next thing I'm going to do, this is going to be kind of tough, and I'll walk you through this, right, best I can. But where does it come from? Why? It's because of delta H makes not zero. Okay, so that's one way to phenomenologically think about why this equation with these chi A's, which is Rayleigh's law, why that really doesn't work. Henry's law is just a band-aid, and then this is cause wrapping, right, to fix the wounded equation that doesn't actually work. Now, and again, why do we want to think of it this way? Here's a justification for why I'm doing this, and that's that delta mixed H is not equal to 0. Now, remember the word phenomenological? Remember that? I brought that up a while ago? All right, that's an equation that just makes sense. And then we use it. All right, so I'm going to do that here. All right, for one, so I'm not going to let delta H be 0, and then I'm going to show you where activities come from. So that's, and it comes from this. All right. Now, the first thing is that I know that enthalpies can be positive or negative. So that's beta. Now, this can be anything. Okay, so again, another dimensionless parameter that makes it work. That still kind of sucks. But so this is going to give us a positive or negative. Because I know sometimes, actually a lot of times with mixed solutions, they actually get cold. Right? Most things like to get hot, but a lot of things actually get cold when it comes to liquids. Okay, now here's a clever thing. You're going to multiply it by the mole fractions of both A and B. That makes sense because if one's 1, the other's 0. Because if a mole fraction of A or B is wrong, there's no solution to begin with. So there should be no enthalpy, nothing's happened, so it's still a glass of water. It's not just exuding heat. Okay, so that just makes sense. Again, it's phenomenological that I would need to have zero when I don't mix anything, and this assures that. Now it needs units, and it needs to be extensive. And remember, H is not H per mole, this is H. So I need to have extensivity, so I can multiply by N, and then it needs units, and I might as well just stick with RT. And remember, beta can fix anything. So if this number is too high, well then beta becomes too low and fixes it. See, kind of bullshit. So that's why I don't like this stuff. Okay, and therefore, okay, I gotta leave myself. So, I'm sorry, I'm not using the board very well. G is nRT chi a natural log of okay. So this is how I'm going to use the fix. So notice I've stopped using activities. I've gone back to my mole fractions, and I'll explain why am I going backward like this. That kind of sucks. Plus beta. Sorry, yeah, okay. Okay, I just didn't leave myself the room I needed. Okay. So again, activities are fixits. They come about from delta H. And when I add delta H, I pick up this term, but notice I backtrack on activities. Because if I include this term, I don't actually need to use activities because this is the fixit. Now what I'm about to do is going to be kind of painful, so you want to start on a fresh piece of paper. But I'm going to show that this in activities, that doing this or doing this, these are exactly the same thing. So I have to prove that this is equal to that. It just has to be molded into the right shape. So I'm going to start a derivation. Yeah, I need a new sheet. I say new sheet? I need a new board. Okay, so equation that goes across the board, right? So you've seen me do that a couple of times. This is one of those times. So you want a fresh sheet, and I can tell you I'm going to do, I think, 6 lines. It's not as copious as it sounds. You got that sort of reference. Anyway, let me see here. I'm going to do 1, 2, 3, 4, 5, 6 lines. So leave about 12 lines free. So turn the page, leave about 12. If you can see that, this is what I'm about to do. The crazy thing is I'm going to start from the top and go halfway, and then I'm going to start from the bottom and reach it. That's what I'm going to do. So here, I'll help you out best I can so you can write this down without running out of room. Okay, so I'm going to start with activity. I'm going to start with my equation for activity and mold it a little bit. Then I'm going to start with the other that guy up there, and then I'm going to mold it into the same thing. That's doing there. And remember that activities is this thing, because that's what I'm going to do next. Leave myself room. Okay, natural log of a plus b is what? Sorry, natural log a times b is, I just gave it away. Yeah, ln a plus ln b. So chi b, ln chi b. What I'm doing is I'm taking a times b apart. Chi a ln this gamma thing, and that belongs to a. I should have put that subscript in it before. Gamma b. Okay. So anyway, again, these are the same thing. I just broke it into 2. Okay. Then there is going to be 1, 2, 3, 4 more steps, but I'm going to start from the bottom. I know this is a little funky, but trust me, this is going to work. It's kind of, this actually, as much as I don't like this stuff, this part is kind of interesting. nRT, so I'm starting with that thing up there, I'm just rewriting it. Part of my pen. ln chi a plus chi b, ln chi b, plus this beta parameter chi a, chi b. Okay, the next step is to actually multiply this by the number 1. It's always clever how that trick works. nRT maybe I shouldn't talk this stuff so much. Because this is actually the only part about Henry's long range law that I actually like. Because I do like phenomenological models, even if they are kind of just generated. Okay, and to multiply by the number 1, I'm simply going to multiply by the mole fraction sum. And you can see now why I like to stick to just A and B. So just you might want to note that if you can, that you just multiply by 1 so that you see what you did. Now I'm going to distribute these things. Sorry, that looks miserable. And RT, IA. All right, notice that these are all the same. So I just got to get to those last 2 terms. Hopefully it's kind of obvious that what I've done is I took a single term. I took this single term and now broke it in 2. That was actually my point. So I've got beta chi A squared chi B plus beta chi B squared chi A. Okay, God, this hurts my arm. Okay, almost done. NRT again. This part, that 4 is, we're ln chi A plus chi B, ln B, chi B, ln chi B. God, my arm hurts. Okay, plus chi A. And did I kind of reverse these? Sorry, I kind of screwed this up. I'm actually doing this term. Sorry about that. Beta chi B squared. Yeah, sorry about that. So anyway, I have to switch these terms. I should have wrote them in reverse. Sorry about that. So this term is this term. So just make a note of that I screwed up. Beta chi A squared. I hear you. Okay, so there you go. That's the derivation. Oh God, what a bloody mess this is. Anyway, the point of this is to show these guys are the same. Stupid, but anyway. Here we go. Okay, almost done. Okay, sorry, I guess we'll get out 5 minutes early, and that's about it. But what I want to do is I'm going to rewrite this thing using this information here, and so that I can see where activities really come from. So, how do I want to do this? Okay, so I'm just going to write down a bunch of relationships with solvents and solvents with this whole activity thing. Let's do solvents first, which will be A as usual. So what I have is ln, sorry. Yeah, ln chi A. Where do I have that? Okay, it's equal to beta chi B squared. And chi A and chi B, of course, related, so I'm going to switch chi B to chi A because that makes more sense. And therefore, gamma is e to the beta chi B squared. Sorry, this is, I have to write a lot of stuff, so this is going to be kind of painful. Okay, now the activity of A was gamma chi A, which is now chi A e to the beta chi B squared. And remember, that's the actual partial pressure of A over the pure partial pressure, right? Remember, and that is ultimately what I put in the natural log, which gives me the entropy. And then I approximated G as just minus T change in entropy. So, anyways, again, this is not approximated by chi A times the pure partial pressure of A, divided by the pure partial pressure of A, which is Raymond's law. Now, since chi B is 1 minus chi, 1 minus, not minus 1, 1 minus chi A, Therefore, the partial pressure of A is chi A e to the beta 1 minus chi A squared. A squared times the pure partial pressure of A. Sorry, it's a little messy on here, it's not so great. Okay, now the point of this is that if chi A goes to 1, let's, what do I got here? If chi A is 1, all right, now if this is true, wait, sorry, what do I want to do here? Now let's let it, if that's true, that's a solid, sorry, I misspoke. If this is 0, right, I don't want chi A to go to 1, that's for solvents. Solvents have chi A's close to 1, solutes have chi A's close to 0, my bad, a little slow on my part. Okay, if that's true, then what I've got is partial pressure is then e chi A e to the beta PA star. Right, I just 1 minus 0 is 1, so I got that. Now notice that what that means is that this is basically Henry's law. Henry's law, where K is equal to e to the beta partial pressure of A star. Right? Let me make sure I got that right. Sorry, I'm a little twisted right now. Okay, so, right. Yeah, that'd be Henry's law. So, remember Henry's law is the mole fraction times just some constant that makes everything work. Right now, if beta goes to 0, then PA is chi A PA star. And what's that? Well, law, Henry's law, Reynolds law. Reynolds, okay, now when Reynolds law works for solvents and solutes, what kind of solution?
Ideal.
Ideal, right? You have ideal and ideal dilute. So this is the ideal dilute, and then this is ideal. So now the point here is that I have a phenomenological reason why I should have a Henry's law constant, which is not the same as the pure partial pressure times the mole fraction. It's been adjusted because there's some enthalpy, right? Enthalpy is non-ideality, because normally in an ideal solution there's no enthalpy of mixing because the interaction of the molecules are the same and they have the same volume. Now, if there is no enthalpy, then there's no reason to have Henry's law, and we'll do D. So there you go. That's kind of perfect. So let me do the same for B, and then we are out of here. Okay, so ln by B to the beta. So this is going to work, right. So this is going to work all the same way. So gamma, sorry, I should have a little a here, right? Sorry, if you don't have that, it doesn't matter. It doesn't matter, right? You can follow this. Okay, and that means the activity of D is gamma B chi D, which is chi D e to the beta chi A squared, which then again is the actual measurement that does not necessarily follow Reynolds law. Okay, and then I'm gonna just do this ditto, and what I have then is PB is chi B. So you can just follow this from your notes. I'm just doing exactly what I did on the other guy. So now these are pretty much exactly the same, right? I just got the A's and B's permuted. All right, now this is where we want to make these approximations. Chi E goes to 1, So again, if my solvent is highly, highly pure, that's what this is really saying. If that's the case, then this term goes to 0.
0.
1, e to the 0 is 1, right? Therefore, PB is chi B, PB star. Okay, which is equal to which law? Yeah, Raoult's law. And if beta goes to 0, PB is, so no matter what, when your solvent is pure, or there's no enthalpy of solution, then everything is ideal. So the solvent, so here's the trick to remembering this, if I have it on the test, which it might, is that solvents are always ideal. They're always going to follow Raoult's law, and solutes not necessarily true. Again, for an ideal, they will. If there's no enthalpy of mixing, which is the result of non-ideality. And if not, if there is such a thing as non-ideality, you have the ideal Raoult solution where you use the Henry's law constant, but Henry's law is based on enthalpy. That's where it comes from. So, okay, I promised you an early exit, I lied. But we do have an extra 2 or 3 minutes, so I don't have anything else to say. We're done for the third test for Wednesday review, and I'm telling you this garbage going to be on there.